Hello and welcome to lesson number 12, solving trigonometric expressions. This lesson has to do with the final steps in solving a trigonometric relationship. Let's say you have some equation which you then simplify to get a trigonometric relationship such as this. Let's say sine A is equal to sine B. If we get down to something like this, you might be tempted to just say, well, that's easy, A equals B. While this is correct, it's not the only solution. Some of you might instead write this as A is equal to the sine inverse of sine B. This is also not correct. It is correct as one of the solutions, but it's not correct in that it's not the full solution. For any such trigonometric expression that you might have, there are multiple solutions that you can have. The reason for this is, of course, the repetitive nature of trigonometric functions. Sine theta, cosine theta, tan theta, sec theta, cosec theta and cotangent theta are all repetitive functions. They repeat in some period. For that reason we call them periodic functions, which means because they repeat, they have multiple x values corresponding to single y values, meaning there is no proper inverse function for these trigonometric expressions. Something like sine A equals sine B does not guarantee that A is equal to B. It rather guarantees that either A is equal to B or A is equal to some repetitive period of B. So let's first get into this first example, sine A equal to sine B, and get into the different values that B can be relative to A. So to do this, we'll first consider a circle. We'll first consider a circle like this. We'll draw out a circle and we'll mark an angle. We'll call this angle, we'll call it theta. So we draw out a circle. Let's draw a circle like this. I'll mark the principal axis in the positive x direction like this. We'll get rid of the circle now, and let's say our angle here is theta. This is theta. Let's focus on what sine theta is. In this case, if this is the principal axis as in the positive x axis, then in this triangle sine theta is this length here. This is sine theta. So what we're looking for is another angle such that the height from the x-axis upward will be the exact same. In this case, if I just extend this line over here and draw this line here such that this angle here is theta, you will see within this triangle we have the same direction upward and the same length sine theta. So this length here is also sine theta, same as this. But what's the angle that's correspondent to this direction? This direction that I've marked here, which angle is correspondent to it? Well, you can see to get to that direction, we could go a full 180 degrees and then go theta degrees in the reverse direction. So that means we go a positive 180 degrees or pi radians and then a negative direction distance of theta. So this angle here, the angle correspondent to this direction, the angle which is here, this angle is pi or 180 degrees minus the angle theta. Here we can see, and we derived this by the way in an earlier video, I'll put a link to it in the top right. Sine theta is equal to sine of pi minus theta. This is clearly evident here. And if we keep rotating and trying different directions, we will see no other direction works out for it without going a full 360 degrees around the circle. Only this direction here, which I've marked as the first one, this theta direction, and the 180 degrees or pi radians minus theta are the two ones that give the same sine theta value. This value here, if I just go do this length which I marked here is the same as sine theta, but you will notice it is in the negative direction. So here actually the value of this theta is negative. So we don't want that, we want the exact same value, meaning the one we're interested in is sine theta is equal to sine of pi minus theta. This could be our other angle B. Let's say we have sine A equal to sine B, sine A equal to sine B. One of the possibilities is of course that A is equal to B. This is the simplest possibility. Another possibility is that A is equal to pi radians minus B, which we have just shown by the fact that sine theta is equal to sine pi minus theta. Another possibility is that we go a full circle like this and then an extra theta degrees. So in this case that would be 360 plus theta, or in radians 2 pi radians plus theta. So we also have that the sine of theta would be equal to the sine of 2 pi plus the angle theta. So given this, if this angle was A, it is angle was B rather, it is also a possibility that A is equal to 2 pi plus B. This is also a possibility. We can have this as well happening. And furthermore, if we go another 180 degrees additionally to that, if we go first to 360 and then we go another 180 and then we go in negative theta, we'll still be facing the same direction correspondent to this direction over here, which had the same sine value. So it is also possible for us to write that sine theta is equal to the sine of, in total what we did here was go 2 pi radians plus another pi radians, so 3 pi radians total, and then minus an angle theta. So here what we have is 3 pi minus theta. And of course this pattern repeats. The next one will be 4 pi plus theta and so on. So A could be 3 pi minus B and A could be 4 pi plus B and so on. You should also notice that this is also possible in the negative direction. If we go in the negative direction like this and then we go an extra theta degrees, we will be facing that same original direction. So then if we go a negative pi radians and another negative theta, we will again be facing in this direction, which will have a sine value corresponding to our original sine theta. So therefore in the negative direction as well, we have other values that we could have. In the negative direction, sine theta is equal to sine of negative pi plus negative theta. So therefore A could also be equal to negative pi plus negative B, which is that. And then if we go another 360 like this in the negative direction, that's 2 pi radians done. But then if we go theta in the positive direction, we are facing in this direction, which is correspondent with that same sine value. So therefore if we go negative 2 pi radians and then a positive theta, that will still give us the same answer. So A could also be negative 2 pi plus B. And you can see again this pattern is going to repeat. A could be negative 3 pi minus B. A could be negative 4 pi plus B, and again the pattern is repeating. If we list out all of these values, you will see something interesting. So one, if I'm just going to write all the values of A in a straight line here, one of them is B in the middle. The next one I'm going to write is pi minus B. The next one I'm going to write is 2 pi plus B. The next one is I'm going to write is 3 pi minus B. I'm going to extend this in this direction, I'm going to comma, and I'm going to go in the negative direction as well. In the negative direction, the first one we come across is minus pi minus B. The next one is minus 2 pi plus B. The next one is minus 3 pi minus B, and it extends in this direction. So therefore we have extensions in both directions, and any of these values could be the value A. So in this case, I want you to notice the pattern here. There's a nice pattern that we can see. Over here we have 1 times pi. Over here we have 2 times pi. Over here we have 3 times pi. If we go and extend this in this direction, if we say this is 1 times pi, this is 2 times pi, this is 3 times pi, this would be 0 times pi. This is negative 1 times pi, this is negative 2 times pi, and this is negative 3 times pi. If you want to establish a common pattern here, we can say if we label each of these as the nth possible solution, I'll call it T sub n. If each of these is labeled T sub n, we can label the middle one as T sub 0, the next as T sub 1, the next as T sub 2, and so on. And in the reverse direction, we can name this T sub negative 1, T sub negative 2, and T sub negative 3. And so on in that direction as well. So here, we can see for each T sub n, we need an n pi. There needs to be n times pi in the front. But then there's this other interesting thing that's happening where we have plus b here, then minus b, then plus b, then minus b, then plus b, and so on. So we have plus b minus b plus b minus b repeating. A function that easily repeats this behavior is negative 1 to the power of n, where n is an integer. When n is an integer, if n is odd, negative 1 to the power of n is going to be negative 1. If n is even, negative 1 to the power of n is going to be positive 1. So here, if we just do a plus negative 1 to the power of nb, you can see that the pattern is matching. if we substitute each of these n's as n equals 0, n equals 1, n equals 2, we can see we produce this set of solutions that we have here. When n equals 0, we have 0 pi plus negative 1 to the 0 times b, which is just 0 here. Negative 1 to the power of 0 is going to give us 1 times b, so which is just b. The first solution is b. Clearly, as we can see, it works. The next one is t1, which is 1 times pi, or 1 pi, plus negative 1 to the power of 1 times b, which is 1 times pi is pi, negative 1 to the power of 1 is negative 1, times b is negative b. So we have pi minus b. You can check for the rest, but of course this is, as we've constructed this from the observation that we already have, it's definitely going to be true. And this is the expression for the nth solution. So here, if we express this in a common way, we can say that a is equal to n pi plus negative 1 to the power of nb, and the condition that we need here is that n is an integer. For all the integer n's, substituting it into this formula will give you one possible solution. So therefore, since every single one of these solutions is possible, we can write every single solution as a common thing like this. You can say that a is equal to n pi minus plus negative 1 to the power of n times b, where n is some integer. It doesn't matter which integer, because any integer will give you a valid solution. If you want a specific integer, you can choose a specific n and then find that value of the solution. So here, in summary, what we have is that if, I'll put an if in the front, if sine A is equal to sine B, we have derived that in this case A is going to be n pi plus negative 1 to the power of n times B for some integer. Doesn't matter which integer, any integer will give you one valid solution, but plugging all the integers will give you every possible valid solution. So here we can see there's an infinite number of valid solutions, but our common general formula will solve for every single one at the same time. You just have to choose some n, that will give you one of the solutions. If you go around choosing every single possible n, that will give you every single possible solution. The next thing I'm going to do, of course, is going to do the same exact thing, but for cosine theta. And for cosine theta, we get another pattern which is similar, but somewhat different in the values that we have in it. If we draw another circle like this, again we mark the principal axis like this, and principal axis, of course, is the positive x-axis. We're going to mark some angle theta, and we're going to consider what cosine theta is. So here we have the angle theta, which means the direction we're interested in is this direction. With this direction, the value of cosine theta is this distance here. This is cosine theta. So we want to find what other angles will give us the same value of cosine. So here if we look, what we need is points on the circle that have the same x coordinate as this point right here. The other point that has the same x coordinate as the first point is this other point here. What is this point? Well, this point is the point such that this angle here is also theta. So here, since we defined anticlockwise rotation as positive angles, this right here is an angle of negative theta. So we have an angle of negative theta over here. So then we can see directly cosine of theta is equal to cosine of negative theta, because here we are going in the clockwise direction and taking the cosine of the same angle. We're going in the anticlockwise direction and taking the cosine of the same angle. Clockwise is negative angles, anticlockwise is positive angles. So therefore here we have that cosine of theta is equal to the cosine of negative theta. So therefore, if cosine of A is equal to cosine of B, one possible solution is that A is equal to B. Another possible solution that we've just found is that A is equal to negative B. So I'll write those down. A is equal to B is one solution, and A is equal to negative B is another solution. If we go around the rest of the circle, we can see within the rest of the circle there's no other angles, no other direction such that cosine of that angle is equal to the same original cosine of theta. But if we go a full circle, a 2 pi radians, then we go a plus angle of theta, you can see this gives us the same cosine amount as we have the same direction that we had originally. So therefore, the cosine of 2 pi plus the angle theta is still going to be the cosine of theta. So cosine of theta is equal to the cosine of 2 pi plus the angle theta. But notice, if we still go a full circle, but now instead of going a positive angle theta, if we instead go a negative angle theta, we again end up in this direction, which also, as we saw earlier, still has the same cosine value. So therefore this thing must also have the same cosine value. What we did to get to this direction is rotate a full 2 pi radians in the clockwise direction and then a negative theta radian distance. So therefore the cosine of theta is also equal to the cosine of 2 pi minus the angle theta. You might see where this is going, but I'll do one more. If we continue circling around and we go full 2 circles, which means we went a total of 2 times 2 pi radians or 4 pi radians, now we can see if we go apply a plus angle theta, we'll still be in the same direction. If instead we go by a minus angle theta, we'll be in that direction. So therefore, the cosine of theta is equal to the cosine of 4 pi plus theta and the cosine of 4 pi minus theta. So we have cosine of theta is equal to the cosine of 4 pi plus theta and the cosine of theta is equal to the cosine of 4 pi minus theta. So here if I write these set of solutions down over here, we have a is equal to 2 pi plus b and a is equal to 2 pi minus b as possible solutions, and then next we have a is equal to 4 pi plus b and a is equal to 4 pi minus b, and so on infinitely, continuing the pattern. Also in the negative direction, if we reverse in the negative direction, we can see going in the negative direction as in the clockwise direction, if we go 2 pi radians and then we go a positive theta, we get the same cosine value. Similarly, if we go a negative theta, we get the same cosine value. So therefore, those are also valid solutions. A could be negative 2 pi plus theta, and A could be negative 2 pi minus theta, and similarly, if we go 2 full terms, we can also say that A is equal to negative 4 pi plus theta and also negative 4 pi minus theta, and pattern continuing so on. If we write this only in a straight line like we did earlier, we can see in the middle we have b as one of the possible solutions. Negative b was also one of the possible solutions up here. And then in the positive direction, the next one we would have to write is 2 pi minus b, 2 pi plus b, and then 4 pi minus b, and then 4 pi plus b. Again, I'm writing this in ascending order so that we can see the pattern. In the reverse direction, what we have is minus 2 pi plus b, and then next one would be minus 2 pi minus b, and then we'll continue the pattern. So here, if you look at the pattern here, we can see something interesting. Here we have 0 pi, here we have 2 pi, here we have 4 pi. In each of these jumps, we have a plus case and a minus case. Here, in the middle, what we have is a plus or minus b. Over here, in this case, what we have is 2 pi plus or minus b. Over here, for this pair, we have 4 pi plus or minus b. Over here, in the other side, we have minus 2 pi plus or minus b. And then the next one, of course, is going to be minus 4 pi plus or minus b. So what it seems to be, the pattern seems to be multiples of 2 pi plus or minus b. So that is the solution for our issue. A could be some even multiple of pi, as in 2 pi times some integer plus or minus b. So if we write this in a common formula, if we call this Tn, we could call this 0th term, we could call this the first term, the second term. This could be the negative first term, the negative second term, and so on. If we write this as a common formula, here we have 0 times 2 pi, and if we write this, we have n times 2 pi plus or minus b are possible solutions for A, where n is an integer. So these are the solutions for the equation cosine of A equal to cosine of B. If I write this in summary, what we have derived is that if we have cosine of A equal to cosine of B, then from this we can say that A must be equal to 2 pi times n, which I'll actually write nicely as 2n pi plus or minus b for an n in the integers. Now here n can be any integer and we will have a solution on our hands. If we want a specific solution, we need to choose a specific n, but n can only be any integer. and for any n integer we will get a valid solution. Here we have a plus or minus, which means we can either choose the plus case or the minus case. For any integer n, choosing the plus case or the minus case will give us one of the valid solutions for this equation cos A equal to cos B. So here again I want you to note there are an infinite number of solutions because n can be any integer and there are an infinite number of integers. There's one more, which is the tan of theta, which we will go on to next. So now considering the tan of theta, again what we're going to do is draw a circle and draw some angle and then use that to try to figure out the relationship of tan with its periodicity. So if we draw this circle out with the principal axis like so, draw this circle with the principal axis like so, and then this is the x-axis. If I label an angle theta like this, here what we have is tan theta is equal to sin theta divided by cos theta, and tan theta here is this length that we have here. This length of the tangent until it touches the x-axis is the length that we call tan theta. So now let's look at its multiples. If we change the angle to this right here, we can see that here, because this line here is a straight line and this line here is a straight line, these two are vertically opposite angles, which means this angle is theta. Considering this length here, this is also a tan of theta. This is tan theta. This is the tan of this angle here, which is 180 degrees plus theta. So it is 180 degrees plus theta, or pi radians plus theta. So therefore the tan of theta is equal to the tan of pi radians plus theta. Some of you might be wondering, what about this thing? If I draw this thing, this is theta, and over here if I draw this tangent, isn't this also the same length? And you're right, the length is the same, however there's a distinction. Over here in this case, we are in currently the second quadrant. Recall, in the second quadrant the only thing that's positive is the sine function. The cosine function and the tan function are negative. So you're right that the absolute value, the length of the line, is in fact the same. However, over here the tan function is negative, over here the tan function is positive. So we have the issue where the sine is different but the absolute value is the same. So no, this is not a valid angle. This angle of pi radians minus theta is not valid for our equalness of tan A and tan B. Because although the length is the same, the actual sign of the value is different because we are in the second quadrant. So here tan theta is equal to tan pi plus theta. If we keep going, same problem over here with this quadrant. This is the fourth quadrant, which again has the same issue of the sign. So we have to ignore that one, and then continuing to circle around, the next place that we have the same tangent value is when we do 2 pi radian turn and an extra theta. So then we can say that tan theta is also equal to tan of 2 pi plus theta. The next time that we have the same thing is when you do a full turn, another half turn. So 2 pi radians plus another pi radian, or 3 pi radians plus an angle theta. So again, you can probably, this pattern is actually easier to spot than the others. Here we have tan theta is equal to tan 3 pi plus theta. Similarly, this will continue forever, and in the negative direction, if we go negative 180 degrees and then plus a theta, we get again the same thing. So therefore tan theta is equal to tan of negative pi plus theta, and this continues in this direction as well. Writing down each of the possible solutions for A in terms of B. A could be B, one possible solution of course. A could be pi plus B. A could be 2 pi plus B. A could be 3 pi plus B, and so on in the positive direction. Similarly, in the negative direction, A could be negative pi plus B. A could be negative 2 pi plus B. My apologies, I forgot the equal sign there. And so on in this direction. Writing all of these in a straight line, you can see the obvious pattern for this one. We have B, and then pi plus B, and then 2 pi plus B, and then 3 pi plus B, and so on in this direction. In the other direction also we have negative pi plus B, we have negative 2 pi plus B, and so on in this direction. Here if we write a 0, this will be 0 pi plus b. So here we can index this as 0, we can index this as 1, 2, 3, and then -1, -2, and so on. So here, if we want to write a common term for each of these, the common term would be n times pi plus b. Simply Tn is n pi plus b. So therefore, in this case, the solution is much simpler. In this case, all we have is that if tan A, I'll actually write that if tan A equal to tan B, then A has to be n pi plus b, where n is an integer. So this is the solution for equations of the form tan A equal to tan B. The solution is that A is equal to n pi plus b, where n is an integer. So there we have the solutions for sin A equals sin B, cos A equals cos B, and tan A equals tan B. We'll now look at a bunch of other different possibilities for things that you might need to use when solving equations, trigonometric equations. These ones are things that we've already discussed, like again they've already been discussed in circular functions and trigonometric identities. However, you might not have seen how to use them to solve problems. So we're going to do some other exercises in order to see how we can use these identities and identities regarding tan A equals tan B, sin A equals sin B, and cos A equals cos B to find the solutions of these kinds of trigonometric equations. So let's go. So let's try and solve this first equation here. We have that half sine 2 theta plus cosine squared theta is equal to 0. A good strategy to follow when trying to solve these kinds of equations is to reduce everything into sine theta, cosine theta, and tan theta if possible. That's a very good strategy, and it tends to work very well in most circumstances. In this case, we can try to reduce sine 2 theta into sine theta and cosine theta. We know a formula for this. We know that sine of 2 theta is 2 sine of theta times cosine of theta, which we can use here, and then that's plus cosine squared theta is equal to 0. In this case, you can see this 2 and this half cut, leaving us with just sine theta times cosine theta plus cosine squared theta is equal to 0. We can now factor out a cosine theta from both of these because, well, there's a cosine theta in both of these. We can write that as cosine theta times sine theta plus cosine theta is equal to 0. So now we have product of two factors being equal to 0. That means that either of them could be 0. So we have that either cosine theta is equal to 0, or we have that sine theta plus cosine theta is equal to 0. One of these two is equal to 0. In the first case, we have cosine theta is equal to 0, meaning that cosine theta is equal to, and 0 in this case we can rewrite in terms of another cosine. Cosine of pi by 2 is 0. So we can write cosine of pi by 2 instead over here. So now we have that cos A equals cos B, and recall, if we have cos A equals cos B, we can easily solve for theta here. Here we have theta, here we have pi by 2. So therefore the possible solutions are that theta is equal to 2 n pi plus or minus this angle, which is pi by 2. So here we have this, for n being in the integers. These are all the possible solutions that we get when we set cos theta being equal to 0. This is one of the possible cases that could happen. The other possible case is that sine theta plus cosine theta is equal to 0. To solve this one, we will try to take the cosine theta to one side and reduce this whole thing into a single trigonometric function. What we're going to do is say that sine theta is equal to negative cosine theta by taking cosine theta to the other side. And then we're going to divide both sides by cosine theta, and again recall, because cosine theta was 0 in the first case, on the second case cosine theta is not going to be 0, because either cosine theta is 0 or cosine theta is not 0. So we're going to assume that in this case cosine theta is not 0. So we can say sine theta divided by cosine theta is equal to -1, provided that cosine theta is not equal to 0, because if cosine theta is equal to 0, we already have one solution, which is anyway going to be true. So if we already have that, that's not a problem, which in this case we are going to eliminate that possibility on the right hand side, because, well, Whether the possibility exists or not doesn't really matter, because we've already taken that possibility into account. So here we can do cosine theta not equal to 0 and divide by both sides by cosine theta. Now we have sine theta divided by cosine theta is equal to -1. This is tan theta, so tan theta is equal to -1. And -1 is the tan of, either we can do negative pi by 2, negative pi by 4, my bad, my apologies. Pi by 2 will give you an infinity with tangent, and here we can either do tan of negative pi by 4, or we can do tan of 3 pi by 4, either of them. I'm going to in this case do tan of negative pi by 4, which in this case we have that tan A equals tan B. We have that tan theta is equal to tan of negative pi by 4. So now we can write that theta is equal to, recall, an integer times pi plus the angle inside, which is negative pi by 4 for m element of integers. So the reason here that I put m instead of n is because I've already used the symbol n to mean something else. In this case, because I don't want to repeat the symbol, I have added a different symbol m. It doesn't really matter, but I want to distinguish between this counting number and this counting number. For that reason, I'm using two different counting numbers. So we have that this is one possible set of solutions, this is another possible set of solutions, but our intersection between these two is an OR operator. So therefore, if we want to combine these two into one single set of solutions, we have that theta is equal to the set of 2n pi plus minus pi by 2 for n element of the integers union with the set of possible solutions of m pi plus, actually I'll consolidate this minus outside here and just say minus pi by 4 for m element of the integers. So therefore this is the final possible set of solutions for our theta angle. It is the first set of solutions or the second set of solutions, which is what the union operator here is for. So therefore this is the kind of effort that you have to do in order to solve equations such as this one. Here what we did first, I recall I told you this is probably going to be a good strategy in most cases, is to try to reduce every single function into sine thetas, cosine thetas and tan thetas. It tends to make our solutions easier to figure out. And then once we've done that, we can then either, if it's possible, try to factorize and get something like this, where multiple factors are multiplied together and equal 0, in which case we can take each individual 0, consider it separately, and then take the union of all the cases as the final set of solutions for theta. So that is the set of solutions for theta in this particular case. Let's now look at a different exercise where we have a different kind of question that we need to solve. So here we have another equation here. We have sine theta plus cosine theta equal to half. Let's try to solve this equation. So here, what I'm going to do here is try to write cosine theta in terms of sine theta. I can easily do this because we know an identity between cosine theta and sine theta. Sine of pi by 2 minus theta is equal to cosine of theta. Similarly, cosine of pi by 2 minus theta is equal to sine theta. I can use either one of these in order to convert one of the sine thetas into some expression of cosine theta, which I'm going to do. I'm going to leave the sine theta alone, and I'm going to convert the cosine theta into sine of pi by 2 minus theta. So I'm going to write here sine of pi by 2 minus theta is equal to half. Now we are going to look at some patterns here. Here we have sine theta plus a sine theta, some angle, sine A plus sine B. Recall we had a formula for this. We had a formula for sine C plus sine D. We had a sum to product formula. If you don't recall it, go back to the trigonometric identities video. It's right there. I might add the timestamp into the card at the top. Check that out. We have that if we have sine C plus sine D, this is equal to 2 sine C plus D divided by 2 times the cosine of C minus D divided by 2. So using this formula here, we can actually simplify this thing into a single sine function cosine function product. What we're going to do is use that formula there to simplify this thing. Here what we have is 2 times the sine of the two angles added together divided by 2. If we add the two angles together, we have theta plus pi by 2 minus theta added together times the cosine of the angle subtracted, which is theta minus pi by 2 minus theta divided by 2. So then this thing is equal to half. Now I know it looks like we just made this thing extremely complicated, but trust me, it's going to simplify nicely. One nice simplification we can see here directly is that this plus theta and this minus theta cancel out, leaving us just a pi by 2 divided by 2 in the middle. So therefore, dividing that pi by 2 by 2, we get the sine of pi by 4. And then multiplied by the cosine of this angle here. What's this angle? Well, here we have a theta minus a negative theta, which is another positive theta. So we have a 2 theta and then 2 theta minus a pi by 2. So here we have 2 theta minus pi by 2 whole thing divided by 2. We have to take the cosine of that one. This is now equal to half. So here I know the sine of pi by 4. We know it. It's a basic non-trigonometric value. It is 1 divided by root 2. So there we have sine of pi by 4 as 1 divided by root 2. I'm going to substitute that in. Over here I'm going to simplify this internal expression as 2 theta divided by 2 as just theta. So we have cosine of theta minus pi by 2 divided by 2 is negative pi by 4. So we have minus pi by 4 is equal to half. Now I'm going to take this thing to this side and simplify this thing even further. So first, 2 divided by root 2. 2 is root 2 squared. So here we basically have root 2 squared divided by root 2, which is just root 2. So here what we have is root 2 multiplied by this. Dividing both sides by root 2, we get that cosine of theta minus pi by 4 is equal to 1 divided by 2 times this root 2 that we divided. So 1 divided by 2 root 2. So this. Now we have cosine of something is equal to something. Because this thing is less than 1, this is a valid cosine, so I can write this actually as the cosine of the cosine inverse of 1 divided by 2 root 2. This is of course valid because recall, even though we can do it in this direction, we cannot do in the other direction. The cosine inverse of cosine of an angle is not that angle, but the cosine of a cosine inverse of some value is that value. So here what we have is that the cosine of theta minus pi by 4 is equal to the cosine of cosine inverse of 1 divided by 2 root 2. So therefore we have cosine A equal cosine B format, which we can then simplify and turn into theta minus pi by 4 is equal to, my apologies, pi by 4 is equal to, recall the identity that we discovered, 2n pi plus or minus the angle of the second one, which is the cosine inverse of 1 divided by 2 root 2, where n is an integer. In this case we didn't have two cases that we had to add together, we just seem to have just a single case. Isolating theta on one side by taking this pi by 4 to the other side, we can write our final solution as theta is equal to 2n pi plus a pi by 4 plus or minus the cosine inverse of 1 divided by 2 root 2 for n being an integer. So therefore this is our final answer in this case. You can see again, when we have these trigonometric equations, we tend to have a whole family of solutions. Here also there's an infinite set of solutions where the infinity is coming from all the possible integers that n could be. So there, once again, this is the solution for this equation, and you can see how we used the identities that we found earlier in the previous lessons of trigonometric identities and circular functions in order to solve this equation here. So there we go. We'll do one more and end this lesson here today. So this last equation we are going to solve is not going to have specific numbers. It's just going to have some random numbers a, b and c, which we are going to leave as unknowns. Now here there's an important condition. It's the condition that the value of c should be less than the absolute value of c should be less than or equal to the square root of a squared plus b squared. We'll see why shortly, but I'm going to throw this out and we are going to prove how we know that that has to be the case. So over here we have some numbers a, b and c. A, b and c could be literally anything, and we have theta. How do we start solving something like this? Well, here for this one at least, there's actually quite an easy way to do it. Let's consider the triangle with a side of a a side of B and a hypotenuse like this. What's the length of this hypotenuse? Well, we have a 90-degree angle here. This is A, this is B. By the Pythagorean theorem, we have that this side length here should be the square root of A squared plus B squared. So there, this side length here is the square root of A squared plus B squared. Let's say that this angle here is some angle which I'll call alpha. You'll see why we're doing this, but for now, we'll just take this as so. So here, the sine of alpha is equal to B divided by the square root of A squared plus B squared. The cosine of alpha is equal to A divided by the square root of A squared plus B squared, as we can see from the opposite, adjacent and hypotenuse. Similarly, the tangent of alpha is equal to B divided by A. Now, I'm going to take this expression I have up here and I'm going to divide everything by the square root of A squared plus B squared. Again, trust me, you'll see why this is going to be something interesting. If I do that, we get A cosine theta divided by the square root of A squared plus B squared plus B sine of theta divided by the square root of A squared plus B squared is equal to C divided by the square root of A squared plus B squared. So here, notice what we have over here and here. This right here is the cosine of alpha for whatever angle alpha is within this triangle which we've constructed here. So here we can replace that and say, instead of A divided by root of A squared plus B squared, we can put a cosine of alpha for whatever the angle alpha happens to be. We don't know what exactly it is, but we know there is some angle alpha such that A divided by root A squared plus B squared is cosine of alpha. And similarly, over here, B divided by root A squared plus B squared is sine of alpha. So we can write plus sine of alpha times the sine of theta. Sine of theta is equal to C divided by the square root of A squared plus B squared. So we have this. On the left hand side, we have cos of one value, cos of another value, plus sine of a value, sine of another value. We have cos A cos B plus sine A sine B. Again, recall from our trigonometric identities, we found that this thing is equal to the cosine of one of the angles minus the other angle. So here, cosine of theta minus alpha. This must be equal to C divided by the square root of A squared plus B squared. Now here I want you to notice something. On the left hand side, we have just a trigonometric expression. Because of this, and because of the fact that we know, for real angles theta minus alpha, cosine of that value should be between -1 and 1. We know that the left hand side is between -1 and 1. Therefore, we know that the right side is also between -1 and 1. Therefore, -1 less than or equal to C divided by the square root of A squared plus B squared, which is less than or equal to the positive 1. Multiplying both sides by the square root of A squared plus B squared, we can see that C is between the negative square root of A squared plus B squared and the positive square root of A squared plus B squared, provided that the angle that we're inputting here, which is theta minus alpha, is a real number, which of course it's going to be because, well, we are dealing with physical angles. So given this, we can simplify this into a nicer form and say that C absolute value is less than or equal to the square root of A squared plus B squared. Again, because A and B are real numbers, A squared plus B squared is a positive real number, meaning that the square root of A squared plus B squared is going to be a positive number, which is why we can do this simplification and say that the absolute value of C is less than or equal to the square root of A squared plus B squared. So here we started with no limitations, and it turns out there is a limitation that we need to have here if we have a real angle theta. For real angles of theta minus alpha, this needs to be the case. So alright, we'll let that be the case and we'll try to solve our equation now. So we are going to take this as being true, that the absolute value of C is less than or equal to the square root of A squared plus B squared, and we're going to carry on with our actual solution. The actual solution is to look over here and see that because we now have that the absolute value of C is less than or equal to A squared plus B squared, this value here is in between -1 and 1. Because this value is in between -1 and 1, this is equal to the cosine of some other angle. So therefore we can write that the cosine of theta minus alpha is equal to, because this is some valid possible value of cosine, we have that this is also equal to the cosine of the value of the cosine inverse of that same value, which is the c divided by square root of a squared plus b squared. Now that we have this, what we're going to do next is observe that on the left we have cosine of one angle, on the right we have cosine of another angle, which means we have cosine of a equal cosine of b, and we're going to recall our pattern. Given this, then the left side angle, which in this case is theta minus alpha, is equal to 2n pi, where n is some integer, plus or minus the angle inside the second cosine, which is the cosine inverse of c divided by the square root of a squared plus b squared. So now, taking this thing to the other side, we can say that theta is equal to 2n pi plus alpha plus or minus the cosine inverse of c divided by the square root of a squared plus b squared. Are we done? No, we're not actually. And here I should also write n is an integer. We're not done because we still have an unknown left in our solution. This thing, alpha, is an unknown. So what we need to do is to try and get rid of this unknown. So here we can get rid of the unknown by using this. The only values that we knew were a, b and c, and we wanted to try to find theta. Over here, this equation here allows us to write alpha in terms of the knowns a and b. Here what we can do is say that b divided by a is equal to the tan of the tan inverse of b divided by a. Using this, we can say that alpha, we have tan a equals tan b format, which means now we can say that alpha is equal to, and here again, to avoid confusion with the other counting number, I'm going to use a different counting number. I'm going to use m. So here, alpha is equal to m pi plus the other angle, which is the tan inverse of b divided by a. Using this, I can now go down here and substitute that theta is equal to 2n pi plus, and then here instead of alpha I have to do m pi plus tan inverse b divided by a. So we have m pi plus tan inverse of b divided by a plus or minus the cosine inverse of c divided by the square root of a squared plus b squared, where m and n are integers. Because recall, again we need n also. We need m in here as well, and m is also an integer. So now what we have here is the final solution to our question actually, which is that theta is equal to 2n pi plus m pi plus the tan inverse of b divided by a plus or minus the cosine inverse of c divided by the square root of a squared plus b squared. I'm going to direct you to one more thing, which is a simplification that we can do here. So here, m and n are any integers, right? M and n are any integers. So here, if n is 0, m could still be any possible integer. So here, if n is 0, we could have 0 times 2 pi, which is just 0, plus either 0 pi's, 1 pi, 2 pi, 3 pi, 4 pi, infinitely that direction, and negative pi, negative 2 pi, negative 3 pi in that direction as well. If n is 1 here, we will have 2 pi and still all of those infinite values. So here if I write the values of n and m, for n equals 0, the possible values are now, if n is equal to 1, what do we have? Well, in the very middle, we have a 2 pi added plus a 0, which means here we have 2 pi. To the right side, we have one more in terms of m, so we have 3 pi, next we have 4 pi, next we have 5 pi, and so on in this direction. In the other direction, when m becomes a negative number, we have 2 pi minus 1 pi, which is just pi. We have 0 because then over here we had negative 2 pi plus 2 pi, which is 0. Then we have a negative pi, a negative 2 pi, and so on. I want you to note here that these two sets are actually exactly the same because there's a one-to-one correspondence between each of them. Each of these elements can be matched up such that we have equal elements in both sets. In fact, for any n, we will have the same exact set, just shifted left and right. Due to this fact, we can actually eliminate one of these two variables and write something else. We can write all we need is some integer multiple of pi over here. We can see in each of these sets all we have is just an integer multiple of pi. So I can actually write that theta is equal to, I'll use another counting number, let's say p. It is just p times pi plus the tan inverse of b divided by a plus or minus the cosine inverse of c divided by the square root of a squared plus b squared. So here p is an integer. Why did I do this last step? Well, it's to illustrate that sometimes our answers could be simplified, because sometimes the periodic nature of certain things that we have in our expressions is actually overlapping. Sometimes the different values of m and n or other periodic numbers that we have added into here, like over here, m and n could be any integer. Sometimes certain combinations of m and n or other integers that you will use in your answers could be overlapping with each other, in which case we can get rid of certain overlaps. In this case, we've gotten rid of this overlap happening here. For every possible n, we are still getting the same exact set, so we can eliminate that thing and write simply as a simpler form, theta is equal to p times pi plus the tan inverse of b divided by a plus or minus the cosine inverse of c divided by the square root of a squared plus b squared. And here, recall, we had the added condition that the absolute value of c is less than or equal to the square root of a squared plus b squared. This condition is necessary if theta minus alpha is a real number. So there, that is the end of our exercises, and it's also going to be the end of this lesson. I recommend you to get your own exercises from somewhere, try them out, maybe Google the answers or ask ChatGPT or some other resource, and do not blindly follow those resources either. Make sure you yourself also understand the results that you are receiving or the results that you yourself are deriving. So I would highly recommend that you just write some random equation. Don't make it too complicated or you might not be able to solve it. Try something simple first and work your way up and solve equations and use that built up knowledge in order to solve more complicated equations. So thank you for watching and goodbye.